Good morning, students. Today, in this lecture series of Hydraulics 1, we study about the velocity, potential, and stream function of the fluid kinematics. In this lecture, first we study about stream function. Okay, so how can we define stream function? Do you know about it? What is meant by stream function? It is defined as the scalar function of space and time such that its partial derivative with respect to any direction gives the velocity component at right angles to that direction. It is denoted by phi and defined only two-dimensional flow. Okay. So in stream function, consider the simple case of incompressible two-dimensional flow in the xy plane. The continuity equation in Cartesian coordinates reduces to du by dx plus dv by dy is equal to 0. This is called as equation 1. Okay. A clever variable transformation enables us to rewrite this equation 1 in the terms of one dependent variable psi instead of two dependent variables u and v. We define the stream function psi as u is equal to d psi divided by dy and v is equal to minus d psi by dx. This is called as equation 2. Substitution of equation 2 into equation 1 yields d dx of d psi by dy plus d dy of minus d psi by dx equal to d square psi divided by dx dy minus d square psi by dy dx equal to 0, which is identically satisfied for any smooth function psi in bracket xy. What have we gained by this transformation? First, as already mentioned, a single variable psi replaces two variables u and phi. Once psi is known, we can generate both u and phi via equation 2, and we are guaranteed that the solution satisfies continuity equation 1. And second, it turns out that the stream function has useful physical significance, namely curves of constant psi are streamlines of the flow. So this is easily proven by considering a streamline in the xy plane as shown in figure. There are streamlines has been shown, psi is equal to psi 1, psi is equal to psi 2, psi is equal to psi 3, psi is equal to psi 4, and the streamlines along the x and y axis are shown. Curves of constant stream function represent streamlines of the flow. Okay. The change in the value of psi as we move from one point xy to a nearby point x plus dx, y plus dy is given by the relationship. When we move from one point, that is the coordinates x and y, and to the nearby point, that is the coordinates x plus dx, y plus dy. These are the coordinates of the nearby points. The change in value of psi as we move from one point to another point. Then we give the relationship d psi is equal to d psi dx divided by dx into dx plus d psi divided by dy into dy equal to minus v dx plus u dy. Along a line of constant psi, we have d psi is equal to 0, so that minus v dx plus u dy equal to 0, and therefore along a line of constant psi, dy by dx equal to v divided by u. Along a streamline, dy by dx equal to v divided by u. We get minus v, that is d psi by dx plus u, which is equal to d psi by dy into dy equal to 0. Where we have applied equation 2, the definition of psi, thus along a streamline d psi by dx into dx plus d psi by dy into dy equal to 0. But for any smooth function psi of two variables x and y, we know by the chain rule of mathematics that the total change of psi from point xy coordinate to another point coordinate x plus dx, y plus dy, some infinitesimal distance away is total change of psi d psi equal to d psi by dx into dx plus d psi by dy into dy. By comparing the above two equations, we see that d psi is equal to 0 along a streamline. The cylindrical coordinates, the continuity equation for incompressible plane two-dimensional flow reduces to 1 divided by r into drvr divided by dr plus 1r dv theta divided by d theta equal to 0. You can get the values from the figure. See the figure, and the velocity components vr and v theta can be related to the stream function psi in bracket the coordinates r and theta through the equation vr is equal to 1 upon r d psi by d theta and v theta equal to minus d psi by dr. Okay, so this is the stream potential or stream function. Then what are the properties of stream function? First is stream. If stream function psi exists, it is possible case of fluid flow which may rotational or irrotational. And the second properties of stream function is if stream function psi satisfies the Laplace equation, it is a possible case of an irrotational flow. Okay. Then velocity potential. What do you know about velocity potential? If it is defined as a scalar function of space and time such that its negative derivative with respect to any direction gives the fluid velocity in that direction, it is denoted by phi. For steady flow, velocity potential phi is equal to f underscore f in bracket x, y, z. These are the coordinates, where u is equal to minus d phi by dx, v is equal to minus d phi by dy, w is equal to minus d phi by dz. Negative sign indicates that flow take place in the direction in which phi decreases. Okay. The velocity components of irrotational flow can be expressed in terms of a scalar function phi x, y, z and t, as u is equal to d phi by dx, v is equal to d phi by dy, w is equal to d phi by dz, where phi is called as the velocity potential. In vector form, it can be written as v is equal to delta phi. So that for an irrotational flow, the velocity is expressible as the gradient of a scalar function phi. The velocity potential is a consequence of the irrotationality of the flow field, whereas the stream function is a consequence of conservation of mass. It is to be noted that, however, the velocity potential can be defined for a general three-dimensional flow, whereas the stream function is restricted to two-dimensional flows. For an incompressible fluid, we know from conservation of mass, delta into phi is equal to 0, and therefore for incompressible irrotational flow with phi is equal to delta phi, it follows that delta square phi is equal to 0, where delta square is equal to delta into delta bracket okay, is the Laplacian operator in Cartesian coordinates d square phi divided by dx square plus d square phi in divided by dy square plus d square phi divided by dz square is equal to 0. From figure you can see the various streamlines and the various velocity vorticity contours in the figure. This differential equation arises in many different areas of engineering and physics. It's called as Laplace equation. Thus, inviscid incompressible irrotational flow fields are governed by Laplace equation. This type of flow is commonly called as a potential flow. Potential flows are irrotational flows, that is, the vorticity is zero throughout. If vorticity is present, for example boundary layer, wake, etc., then the flow cannot be described by Laplace equation. For some problems it will be convenient to use cylindrical coordinates r, theta and z. In this coordinate system, the gradient operator is delta blank bracket equal to d blank bracket in divided by dr into er plus 1 upon r into d blank bracket divided by d theta into e theta plus d blank bracket divided by dz into ez. So that delta phi is equal to delta phi dr ex er plus 1 divided by delta phi divided by d phi theta e theta plus d phi divided by dz ez, where phi is equal to phi in bracket r, theta and z. Since v is equal to v r e r plus v theta e theta plus v2 e z, it follows for an irrotational flow with v is equal to delta phi. Vr is equal to d phi dr, v theta is equal to 1 upon r into d phi by d theta, vz equal to d phi by dz. Also, Laplace equation in cylindrical coordinates is 1 upon r into d divided by dr in bracket r into d phi by dr bracket complete plus 1 upon r square d square phi divided by d theta square plus d square phi divided by dz square is equal to 0. Let's take one example. The two-dimensional flow of a non-viscous incompressible fluid in the vicinity of the corner of figure is described by the stream function psi is equal to 2r square sine 2 theta, where psi has unit of meters square per second, where r is in meters. Assume the fluid density is 10 cube kg per meter cube and the xy plane is horizontal, that is, there is no difference in elevation between point 1 and 2. Find first, determine if possible the corresponding velocity potential, and second, b, if the pressure at point 1 on the wall is 30 kilopascal, what is the pressure at point 2? So by this given data we can draw the diagram and we see what is the condition for the data. The solution, the radial and tangential velocity components can be obtained from the stream function as Vr is equal to 1 upon r into d psi by d theta equal to 4r cos 2 theta, and phi theta is equal to minus d psi divided by dr equal to minus 4r sin 2 theta. Since Vr is equal to d psi dr d phi divided by dr, it follows that d phi divided by dr equal to 4r cos 2 theta, and therefore by integration phi is equal to 2r square cos 2 theta plus f1 theta. Let's call it as equation 1, where f1 theta is an arbitrary function of theta. Similarly, V theta is equal to 1 upon r d phi by d theta equal to minus 4r sin 2 theta, and integration yields phi is equal to 2r square cos 2 theta plus f2r. Let's call it as a equation 2, where f2r is an arbitrary function of r. To satisfy both equation and 2, the velocity potential must have the form phi is equal to 2r cos theta plus c. Okay, where c is an arbitrary constant. As in this case, for stream functions, the specific value of c is not important, and it is customary to let c is equal to 0, so that the velocity potential for this corner flow is phi is equal to 2r square cos 2 theta. Okay. Then second, since we have an irrotational flow of a non-viscous incompressible fluid, the Bernoulli's equation can be applied between any 2 points. Thus, between point 1 and 2 with no elevation changes, P1 divided by lambda plus V1 square divided by tau g is equal to P2 divided by lambda plus V2 square divided by tau g, or P2 is equal to P1 plus rho divided by 2 in bracket V1 square minus V2 square. Let's call it as a equation 3. Since V square is equal to VR square plus V theta square, it follows that for any point within the flow field, V square is equal to 4r cos 2 theta square plus minus 4r sin 2 theta square. By taking the values from previous, we get V square is equal to 16r square in bracket cos square 2 theta plus sin square 2 theta, which is equal to 1. So V square is equal to 16r square. These results indicates that the square of the velocity at any point depends only on the radial distance, that is r, to the point. Note that the constant 16 has units of s minus square. Thus, V1 square is equal to 16 s minus square into 1 meter bracket square equal to 16 meter square divided by s square, and V2 square is equal to 16 s minus 2 square into 0.5 m bracket square equal to 4 meter square divided by s square. Substitution of these velocities into equation 3 gives P2 is equal to 30 into 10 raised to 3 Newton per meter square plus 10 raised to 3 kg per meter cube divided by 2 into bracket complete bracket 16 m square divided by s square minus 4 m square divided by s square. By solving these, we can get the value of P2 is equal to 36 kilopascal. Okay. So, thank you very much. In this lecture, we studied about velocity, potential and stream function, and also we solved some problems related to the velocity function and stream function. Okay. Thank you.